The next speaker is our own Swastik Kopparty.
Okay. Okay, great. So I'll start. So I'll okay, so I'm going to talk about the complexity of multiplicative characters over finite fields, and I'll talk about this complexity in two regimes. One in the language of computation, arithmetic computation, and the other in the land of polynomials. Okay, so I'll quickly introduce the main character for the talk, and all right, the main character for the talk, and right, and then I'll formulate the kind of questions that I want to try to answer, and then I'll answer them. Okay, so I'll always work in the field f2 to the n, the finite field on 2 to the n elements. Okay, and so let me also assume that 3 divides 2 to the n minus 1, so that the cardinality of f2 to the n cross is divisible by 3, and so in this case I know that there is a multiplicative character of order 3, which I'll call the cubic character. Okay, so the cubic character is this map chi, which maps f2 to the n, well, cross, sure, to 1 omega square, which are the cube roots of unity sitting inside the complex numbers. Okay, and and I'll also be interested in the other cubic character, which is the f2 to the n valued cubic character, which maps. So I'll call that lambda, that maps again f2 to the n cross to the same set 1 omega and omega square, the cube roots of unity, but this time they'll sit inside f2 to the n. Okay, and so if you remember, so this lambda has a simple formula. This it's given by the formula lambda of x is just x to the power 2 to the n minus 1 over 3. Okay, and the property of this cubic character, I mean, is well, so the same holds for both chi and lambda. So chi of AB is chi of A times chi of B. It's a homomorphism, and also chi of A is 1 if and only if A is a perfect cube in f2 to the n. Okay, and the kind of thing that I'm interested in is how complex is this function chi to compute. Okay, so can you give me simple formulas that calculate chi, and along the way we'll also study how much chi correlates with polynomials over f2 to the n. Okay, so I'll quickly introduce the kind of things that we'll compare chi against. Okay, great. So I'll start off with the polynomials. Okay, so I want to consider polynomials over f2, or rather f2 polynomials and view them as functions on f2 to the n. Okay, so okay, so these are okay, so first informally, so f2 to the n is a vector space over f2. It's of dimension n, so we can view f2 to the n as f2 to the n. Okay, so this is going to be important, the spacing. Okay, so good. So once it's f2 to the n, we can consider n-variate polynomials over f2 and ask and consider these as functions on f2 to the n, and ask how much do functions of this kind correlate with the function chi. Okay, and so that is exactly the question that I want to formulate now. So so for that I'll make a definition which is the f2 degree of a function.
So now you explain the relation between special type of polynomials in the field and this multivariate polynomials.
Right, exactly. So I'm going to look at functions defined over f2 to the n, and I'm going to define a notion of f2 degree for them, which is the degree of that as viewed as a polynomial over f2. Okay, so the f2 degree of a function f, which maps f2 to the n to f2, is defined as follows. Okay, so first pick a basis. Okay, so my definition is going to be arbitrary in the sense that there will be choices of basis, but at the end everything will not depend on the basis, so it will be a decent definition. Okay, so we pick a basis, and that makes f2 to the n the same as f2 to the n. Okay, then I say the f2 degree of f is d if there is a polynomial of degree d in n variables over f2 that computes the function f. Okay, so if there exists and okay, good. So so it's the smallest such d. So f2 degree of f is the smallest d for which there exists a polynomial of degree d such that p equals f. Okay, great. So the observation to make is that this definition of f2 degree of a function is independent of the basis that I chose here. Okay, so okay, and in a minute I'll give you another definition of f2 degree which makes it clear that it's independent of the basis. It will be completely invariant. Okay, so this is one notion that I want to look at. Another notion that I want to look at is just basically the same thing, but it's now for functions from f2 to the n to f2 to the n. So the f2 degree of function f from. Okay, so the definition is again very similar. I'll pick bases on both sides, okay, arbitrarily, and then I now look for representations of f as a tuple of n polynomials in n variables over f2. So if there exists p1 etc. pn in such that the tuple p1 up to pn equals f, and the degree of pi's are all less than or equal to d. So for all then I say that the f2 degree of this function f is at most d. Okay, so okay, and again just for a very similar reason, this is independent of basis. Okay, and so the right, and so the thing that I want to look at is how functions of low f2 degree, how much they can compute chi, how much they correlate with chi or lambda. Okay, and so that's the kind of thing that I want to formulate. So I'll formulate two versions of this. The first one is so I fix some d, then how large can the following quantity be, which measures the correlation between this. Okay, so I'll take the expectation over a random x in f2 to the n of chi of x with -1 to the f of x, where the f2 degree of f is at most d. Right? So this is question 1 that I want to try to study.
Why did you restrict to cubic character and not finite order character?
So it will turn out, so for me it will be important that I have a bounded order character.
Okay.
Right. So I just instantiated to 3 just for, yeah.
3 was a magic then.
No, 3 is not magic. Well, 3 had to be odd, I guess, and that's it. Yeah. Okay, but I won't be able to say things about general multiplicative characters. Okay, good. So this is one kind of question that I want to ask and answer. So another kind of question is the following. So I fix. Oh, right. So again, I fix D. Then how large can the following be? So I'm now looking for a tuple of functions, or a function from f2 to the n to f2 to the n that computes lambda. So how large can the probability over a random x in f2 to the n that f of x equals lambda of x, where degree of f is at most d. Again, the f2 degree. Okay, so the first okay, so the first thing I want to say is that, okay, so by studying questions like this, you can answer questions like this, and vice versa also. Okay, so if you can say that, okay, so in fact let me make something more precise. Okay, so ideally what I would like to say is that something like this is very small.
There's a phenomenon of self-improvement there again, which is special in some sense.
Right, and that happens only in this line. Yeah, right. So ideally I want to prove something like this, which says that chi is uncorrelated with f. So all the goal of my formulating it this way, or to formulate this question, was to get a question that has some extra self-reducibility property. So this witnesses the pseudo-randomness of chi in some sense. So this is just another formulation of that, and the best that I can hope for this quantity to be is 1/3 plus little o1. Okay, so let me explain why. So I'm looking for functions of low f2 degree that compute. Huh? Oh yeah, it's at most. So I want to show this. I want to show this, and I want to show this. Good. So I mean, lambda is a function that takes only 3 values. So it's very easy for me to come up with a function that computes lambda on at least 1/3 fraction of the points. So I would consider lambda to be pseudo-random against functions of low f2 degree if it is not the case that functions of low f2 degree can compute it any better than this fraction 1/3. Okay, so this is a statement that I would say that, oh yeah, lambda is pseudo-random against functions of low f2 degree. Okay, and so a statement like this easily implies a statement like this, and vice versa. But this is the kind of formulation that I want to study, because this affords itself a self-improvement. Okay, and I'll talk about that in a second now. Okay, so but before I do that, I'll now talk about the model of computation, arithmetic computation over f2, and also formulate another statement about the complexity of chi and lambda in that language. Okay, so arithmetic circuits is what they're called over f2. Okay, so this is a model of computation that, so it's a way of specifying functions. Okay, and all right, so and they're defined as follows. So I mean, you have your input wires, and you take your input variables x1, x2, etc. up till xn into them. Okay, and then you're allowed operations of the form addition and multiplication over f2. Okay, so all wires in this picture will carry elements of f2 on them. Okay, so So for instance, I could say, okay, I want to now add this subset of input variables, okay, and then I could take another subset of input variables and multiply them, and then I could take another subset of things that I've already computed and add them. Okay, so this is a way of specifying algebraic algorithms where where I say, well, I want the sequence of operations, additions, multiplications, etc. Okay, and so this is what I'll call an arithmetic circuit. And it has a quantity called depth, and it has a quantity called size. Okay, and size is the number of operations that I've used. And depth is the depth of the longest computation starting from the input variables going up to one of the output wires. Okay, yeah, depth is the depth.
So your circuits, there are 4 operators, and or not and not.
Right, but
Or just because, okay, yeah.
over f2 plus n times are enough to get everything I want. Yeah. So it's also equivalent to the model of computation where you're allowed AND gates. So you think of these as Boolean inputs, then you're allowed to take the AND of as many variables as you want, the ORs of as many or variables or previously computed things as you want.
I just want to make sure what you're talking about corresponds to what they call AC2 circuits.
Exactly, this is exactly AC0 parity, right? AC0 with parity gates or AC0 with mod 2 gates. Okay, so one has
It comes with parameters d, the depth.
right. So 0 meant the depth is a constant, right? So right. Okay, good. So
No, the depth is constant, the size is polynomial.
the size is polynomial.
So why is the depth constant? That's very restrictive.
Right, because for depth getting too large, people are unable to say anything, and that's why this. Yeah, right. Yeah. Okay, great. So yeah, so this is another name for it, and so in what I'm going to talk about, I'm going to focus on circuits of depth, which is a constant, and size, which is say polynomial or small. Okay, and then having set up this model of computation arithmetic circuits over f2, then you can ask, can an arithmetic circuit over f2 compute the function lambda?
When you say polynomial, is polynomial what, in n?
Polynomial in n, yeah. Okay, so I mean, so another question of that kind which I want to ask and answer is, so I fix depth d, it's a different d, and okay, right, and I guess right. Well, how large can the following be? Yeah. And I ask for the probability that over a random x in f2 to the n, that c of x, which is going to be an arithmetic circuit, equals lambda of x, right, where c is an arithmetic circuit of depth d.
Suppose you ask that you actually compute all the values accurately, then can you do much better?
No, so I can't do much better, and in fact what will end up happening is that I'll first show that you cannot compute it on all values, and that will amplify itself to not being able to compute it on most values or even a noticeable fraction of values. So where C is an arithmetic circuit of depth d and size at most n to the order 1, say, I mean. Okay, and so the best that we can hope for here is 1/3, because again an arithmetic circuit can just compute, I mean, lambda takes only 3 values. So ideally I would like to show it's at most 1/3 plus little o1. Okay, and so and a very old fact in circuit complexity due to Razborov-Smolensky says that if you want to answer questions like this, if you want to understand arithmetic computation and prove that arithmetic computation is limited in powers, then it suffices to answer questions of this form.
Are you saying that the circuit complexity and polynomial complexity are the same thing?
The circuit complexity and polynomial complexity are roughly the same thing. There are a few small losses on either side, but these kinds of questions will
So they're not just analogous. You can go from
yeah, formally one can translate statements of that form to statements of that form. From that form to that form, and actually the other way too. Okay, great. So now I'll sort of outline how one proves this.
And now you should give the highlight, which is really about the degree of this polynomial. This is the
Oh, right. Okay, good. So
the most exciting part.
okay, great. So in fact I haven't even stated the theorem. So maybe I'll state the theorem and then we'll get then I'll start proving things, right? Because I didn't.
First to state the theorem, then you give people's attention.
Okay, so first I want to check. So are the questions clear? I mean, just okay. Okay, great. So the theorem that I want to state now is we'll talk about both those settings, and it will say that oh, indeed what I wanted to prove is true. Okay, so there is an epsilon greater than 0 such that for d equal to n to the epsilon, we have that the character sum bound up there holds. So the expected value over a random x in f2 to the n of is at most n to the minus epsilon. So for polynomials of degree up to n to the epsilon, or for functions of degree of f2 degree at most n to the epsilon, the multiplicative character does not correlate with such functions. So again, so for f okay, so that's one, and the second statement is that so in this bottom setting, exactly the same kind of thing. So again, d equals n to the epsilon, then the probability that lambda of x equals f of x is at most 1/3 plus n to the minus epsilon and so again, remember, in this setting f is a function from f2 to the n to f2 to the n, so it's a multi-valued or many output bit function. Okay, okay. So before going on, I also want to say, okay. So I mean, if I first took the statement and try to prove it, by hand directly, the first thing that I would try to do at least is I would take it and raise it to a very high power and Cauchy-Schwarz a lot. Okay, and so okay, and so when one tries to do that, so I guess this is a remark. Oh, good. Van der Corput differencing. So by Van der Corput differencing.
So let's see. Suppose you wanted to try to tackle this using fancy algebraic geometry.
And
you would put f of x equals a constant, and you're summing a character that's some variety. The trouble here is you wouldn't know non-singularity. Is that the point? You would expect square root cancellation if there's no correlation or nice function. So is that the point here? You have no. Have you tried?
Right. So it's not even close to non-singular because this is viewed over f2.
Okay, so that's
very low characteristic.
still. If you keep the degree low, I don't know.
Oh, right.
I'm just asking.
No,
When somebody writes something like that, it looks very similar to multiplicative character against an additive character on with a polynomial condition, which is there are theorems of that type. If f is
Well, no, I mean over f2 to the n, right? The degree becomes close to 2 to the n. If you view it, if you view,
But you can't apply Weil.
then you can't. Right.
No, but there is a theory of torses which allows you to go to the base field. No, that's exactly. I'll show you.
Okay.
But that's for special sums, which allows you to go to the base field and get square root on the base, not on the extension.
So it'll be.
But you need some conditions on f, which I'm sure you don't know.
Okay.
Yeah, I'm sure it's not. You're taking out the f. It's horrible. You need some non-singularities.
So as I was saying, right, so van der Corput differencing and finally at the end applying the Weil bounds, then this gives the statement for d being much less than log n, and this just is what it is. And right, so okay, so another is that, so let me actually reformulate this statement
Way down for what?
for the multiplicative character. So after
There you go to the f2n setting.
Yes, I just want to know multiplicative character over what? So exactly what way? What you use?
oh, that the chi of g of x, where g is a low degree polynomial over f2 to the n, is bounded.
So you are using, but I'm thinking more of a several variable. Okay.
Right.
Yeah, but you have a multiplicative character, right? The ring is not with multiplicative character.
No, they are,
There are, okay, there are extensions.
but they will have assumptions which I'm sure are not sense.
Okay, so the second statement, thing that I want to say is that, so let me quickly reformulate this in terms of polynomials over f2 to the n, univariate polynomials over f2 to the n. Okay, so another way of saying exactly this statement is the following. So let g of x in f2 to the n of x, so it's a univariate polynomial over f2 to the n, be of the form g of x is equal to summation ai x to the I, where i's are very restricted. Okay, so if you take I and write it in base 2 as an integer, and then you look at it, look at the number of non-zero, so the number of ones that you see in it, this is the Hamming weight of I written in base 2, restrict that to be at most d. Okay, so we look at polynomials which are sums of only certain monomials, then the claim is that okay, so then the claim is that when you look at the expected value over x in f2 to the n of chi of x minus 1 to the trace of g of x, then this is bounded by n to the minus epsilon. Okay, so effectively what I said was functions of low f2 degree, functions of f2 degree d are exactly functions that can be written in the form trace of g of x, where g is a function of this kind. Okay, so this is exactly, this is another just a reformulation of this statement, that right, this is just a reformulation of this statement. So it talks about the correlation of chi with the traces of polynomials over f2 to the n of a certain kind. I mean, these are not low degree polynomials over f2 to the n, but these are polynomials over f2 to the n of a certain kind. So to contrast this with say the usual Weil bound would say the expected value over x in f2 to the n of chi of x minus 1 to the trace of g of x is small, where g is a function, where g is a polynomial of low degree. Okay, so it would talk about so the usual Weil bound would talk about this setting where g is a polynomial of low degree over f2 to the n. So this statement is talking about g is a polynomial of with only certain monomials appearing in it. Okay, great. So now I'll try to work towards the proof of these statements. Okay, so first, so as I said over there already, this statement would imply that statement. So I'll only focus on this statement, and this statement has a self-improvement property, and so that's what I'll just quickly state now. So suppose I knew that probability that lambda of x equals f of x is at most 1 or 0.9. Okay. So suppose I know that no function of low f2 degree can compute lambda on more than 0.9 fraction of the inputs. Okay. Then I want to say that knowing such a statement can amplify itself into a statement of this kind with a slightly higher value of d. Okay. Okay, so let me, so if I call this star, then and this is star star, then star star implies star is something okay, and so I'll just briefly outline how this is done. So the main idea is that well, lambda has this property that lambda of xy is lambda of x times lambda of y. So suppose one had a function f that computed lambda on a large fraction of inputs x, then I can take f and do something to it by evaluating f not only on x but f on x y's for various y's, and combine the answer in some way and try to get it. So good. So what I want to say is, so suppose probability that lambda x equals f prime x or f of x is greater than 0.9, then consider f prime of x, which looks like this, but I won't tell you exactly what goes into it. Some q of f of x a1, f of x a2, f of x at for suitable ai's and q, and in fact you should probably take powers of x too, but okay. So so there is a function of this form which has the property that lambda of x equals f prime x is at oh right, good, I messed up, right. So 1/3 plus epsilon. Then if you had a function that right, so it was proof by contradiction. I wanted to assume this and prove this. So suppose not this. So I had a function which computed it on more than 1/3 plus n to the minus epsilon fraction of the points. Then I would take that function and do something to it and produce another function that computes lambda on more than 0.9 fraction of the points. These are one. This is over 3. Yeah, right. Then for suitable ai and q, then we get that the probability that f of x equals lambda of x is at least 0.9. Okay, so right, so the reason for shifting to this version of the statement is that it can amplify itself, and so ultimately what I really want to show is just a statement of this form, that it's that you cannot have f that computes lambda on almost all of the inputs x. Okay, so now I'll quickly give a quick outline of how one proves a statement of this kind. Okay, so this is based on the Razborov-Smolensky method again. Who long ago gave some very nice arguments that proved that certain functions cannot be well approximated by polynomials, which is a statement very much of this kind. Okay, so before I describe the method, I'll make some very abstract remarks about very abstract remarks about how one proves that a function has high complexity. Okay. Okay. So yeah, so very abstract. So I won't formally define anything, but this will end very quickly in 5 minutes. So bear with me. Okay. So I'll define. Okay, good. Okay, so here's an observation that not all functions can have high complexity. Okay, yeah. Because that's my definition of complexity almost. Not all functions can have low complexity, right? Yeah, I mean the other statement is also true, but so not all functions can have low complexity because, well, there are only so many functions which have low complexity, and there are a lot of functions. Okay, so this is observation 1 that gets us going. Okay, so I haven't defined complexity, but I'll give you a very concrete theorem just after I state all this. Okay, so I'll make a definition. Is again informal. So I'll call a function f versatile if using that function f you can compute all other functions with low complexity. So f is versatile if using f one can compute all functions. In low complexity. Okay, so for example, suppose I allowed you to get the value of f for free, and having done that, you can now compute all other functions with low complexity. Then I call f versatile because it's usable and it's usable for computing all other functions. Okay, so then observation 2 is that f cannot have low complexity. Because if it did, then all functions would have low complexity, and that violates observation 1. Okay, so I guess maybe nobody is on the same page. But
when you write compute all functions in low complexity, that means using f and a low complexity thing.
Yeah.
You can compute all functions. Period.
Yeah.
Okay.
Right. That's what I meant. Right. Right. And so having made that definition, now it should be clear that f cannot have low complexity itself, because if f did have low complexity, then taking this low complexity thing along with some more low complexity stuff, you got every function f.
So in the definition, in low complexity, it actually refers to the verb compute, not to the noun functions, right?
Right. One can compute all functions, compute using low complexity every function.
There's an efficient reduction to f.
I grew up there now. Go ahead.
Right. Okay. Great. Easily. Yeah. Okay. Great. So now I'll make a theorem that states that the function lambda is versatile in a suitable sense, and so that will be precise, and then I will show you why that implies that lambda cannot be lambda has high complexity in that sense. Okay, so the theorem is that lambda is versatile. So I'll first state it slightly inaccurately, but it will be precise again when false. But okay, so it says the following. So for every function f from f2 to the n to f2 to the n, there exists g and h of which are also functions from f2 to the n to f2 to the n. Of f2 degree at most n over 2. that is low complexity, because right such that f is equal to g times lambda plus h. Okay, so it says that every function can be computed using lambda and some low complexity stuff, which is g and h. So maybe I should have said this. So every function from f2 to the n to f2 to the n has f2 degree n, and most functions, in fact a random function has f2 degree n. So asking that g and h have f2 degree at most n over 2 is saying that they are low complexity. I mean, it is a statement. So every function can be computed using the help of lambda. Okay, so what is actually true is not that, but it is almost that. So I'll add on top, there is a vector space V sitting inside the space of all functions from f2 to the n to f2 to the n with dimension of V not very big. It's at most 0.1 times 2 to the n. This is dimension as an f2 to the n space, such that every function f, for every function f there exists g and h of f2 degree at most n over 2 and an e sitting inside V, such that f is g times lambda plus h plus e. Okay, so so this is also pretty versatile. So V is a low dimensional space. Using low dimension and some functions of low f2 degree, I can produce and the function lambda, I can compute any other function f. Okay, so having obtained a statement of this form, one can get, having obtained a statement of this form, one can prove that lambda has that property over there. Okay, and so I'll quickly outline why that's true. Okay, so suppose I won't do, I mean, any this is just an outline. Okay, so suppose there was an f such that probability over a random x, f of x equal lambda of x on at least 0.9 fraction of the inputs. Okay, then so I'll let S be the set of such x where this happens. Okay, now so what I know is that on the set S, f equals lambda. So on that set, oh, so maybe f was a bad choice. Let me call it p. Okay, so I know that on the set S, lambda is identical to the function p. So if I take an arbitrary function and I know it has a representation in terms of lambda in this way, I know now on the set S that arbitrary function has a representation in terms of p. Okay, so the conclusion is for every f restricted to S is of the form g times p plus h plus e, where g and h have low f2 degree and e is in V, and oh right, and so suppose there was a p of f2 degree right. So I said that right. So I mean, I know that on this set S, p equals lambda, and I know that any function f on the whole space can be represented easily in terms of lambda. So now it can be represented easily in terms of p, because p equals lambda on S. So but this gives you a bound on the size of S. So the number of different functions, so the dimension of the space of functions on S is therefore bounded by the dimension of the space of functions that can be represented here. The space of functions that can be represented here, well, p is a function of f2 degree at most n to the epsilon, g is a function of f2 degree at most n over 2. So their product is, well, this is a product over f2 to the n, but it's a bilinear form over f2. So their product is f2 degree at most n over 2 plus n to the epsilon. h is a function of f2 degree at most n over 2, and E comes from a low dimensional space. So it's at most the dimension of the space of functions of f2 degree at most n over 2 plus n to the epsilon plus dimension of V, and this is small. On the other hand, the dimension of the space of functions on S is simply the cardinality of S, and so what all this means is that the cardinality of S is small. Okay. So the cardinality of S is at most this thing which is small and that thing which is small, and so this gives you a complex. So this says that the size of the set S where p equals lambda is small, and this is exactly what I wanted to show. Okay. So this is the this was the sense in which versatility implied a complexity lower bound. Okay. So what I'll talk about in the next 5-10 minutes, or maybe 5 minutes, or maybe what I may not talk about. This is right, is how one shows that lambda is versatile. Yeah. So okay. So it's based on a fact which I alluded to earlier. So f, which is a function from f2 to the n to f2 to the n, or maybe I'll call it g, has f2 degree at most d if and only if g of x, if you write it as a polynomial summation ai x to the I, where I goes from 0 to 2 to the n minus 1. So take g and interpolate it as the unique univariate polynomial of degree at most 2 to the n minus 1. When you write it like this, ai is 0 whenever the weight of I is bigger than d. So functions have low f2 degree if and only if they are linear combinations of monomials x to the I, where I has Hamming weight at most d when you write it as an integer in base 2. Okay. So and I now have a sort of so this is the cleaner characterization of f2 degree that I want to use when I do my representation over here. So I want to represent every f as g times lambda plus h plus something low dimensional. So g, so g I know is a function of the form summation ai x to the I, where i's are restricted. They are only restricted to have Hamming weight at most n over 2. Same for h. So I want it to be summation ai x to the I times over I with weight of I less than n over 2 times lambda, which I know is x to the 2 to the n minus 1 over 3. So now I use the explicit form that I know for lambda, plus h, which is going to be a function of a similar form, some bi x to the I, weight of I at most n over 2 plus low dimensional. Okay. And so I mean I want to represent every function f like this. So my strategy is I'll take f, I'll write it as a polynomial over f2 to the n. It's written as a sum of monomials, and then I just look deep inside and try to find such a representation. So I won't get in. So this is so whatever goes on in here boils down to the following simple combinatorial fact. So I'll just state that fact now, which has nothing to do with f2 to the n or anything else. Okay. So combinatorial fact. So we're changing lands completely. Let's go to z 2 to the n minus 1. This is integers mod 2 to the n minus 1. Okay. And let s sitting inside z 2 to the n minus 1 be the set of all integers I such that the weight of I is at most n over 2. Okay, so this is a set, the size of S is roughly 2 to the half of 2 to the n, because z2 to the n right, because z2 to the n minus 1 has size 2 to the n, and we are looking at integers, n bit integers with having weight at most n over 2. So the size of S is about half of 2 to the n. Then okay, and I let alpha be the number 2 to the n minus 1 over 3 in z2 to the n minus 1. Okay, so then the claim is that S union S plus alpha. So S is a set of size half of z2 to the n minus 1. S plus alpha is also a set of size half of z2 to the n minus 1. I'm taking S, I'm translating it, I'm taking the union of these two sets. Then the size of this is greater than 0.8 times 2 to the n. So S plus alpha is far away from S. The size of S grows when you shift it by alpha. Okay, and so this fact is exactly the same as this if you look at it carefully. And this is exactly what you need in order to prove this kind of statement. And once you know that this is what you want to prove, yeah, so I don't have a very insightful proof of this, but this is once you know you want to prove it, nothing can stop you, right? So okay, so I'll wrap up with some open questions, and that's it. Okay, so we have just 5 minutes for lunch. I'll keep this. Okay, so the number one question is, can you make these n to the minus epsilons into 2 to the minus n to the epsilon, 2 to the minus n to the epsilons? Okay, so is it true that okay, so I'll state it in for just one of them. The expected value over x of chi of x times minus 1 to the f of x is at most 2 to the minus n to the epsilon when the degree of f2 degree is n to the epsilon. Okay, and so at the moment this is n to the minus epsilon, even 1 over n square would be very impressive. And so if one can get something something sub polynomial in n, 1 over n to the little omega of 1, then this would start having complexity implications. It would start saying that and complexity very general complexity implications of the form that randomized algorithms are not more powerful than deterministic algorithms with respect to arithmetic circuits. So arithmetic circuits that use randomization are not more powerful than arithmetic circuits that use that don't use it. Okay, so this is one. So this is a very nice question, I think, and it just should be true, because very good philosophy is well, if two natural algebraic things don't correlate for any obvious reason, then they don't correlate at all, because right, so this should be true. It would be nice to see a proof or to see a disproof also. Yeah. Okay, so another statement, another question that I don't know how to answer from this is the correlation of low degree polynomials with the inverse. Okay, so this is related to the complexity of computing the inverse. Here I talked about the complexity of computing lambda, and now I'm talking about the complexity of computing the inverse over the finite field. So is it true that the same setup, except now I ask that the correlation of f of x is with minus 1 to the trace of x inverse? Well, is this less than little o 1 even, or less than 1 I think is a good question, right? Yeah. No, less than 1 I know. So less than 1 minus epsilon. Okay, and because of similar random self-reducibility things, if you prove less than 1 minus epsilon, this makes it less than n to the minus epsilon. So right, so even the question, yeah, this less than 1 minus epsilon is a nice question. Is it true that low degree functions, functions of low f2 degree are uncorrelated with the trace of x inverse? Right, so again. So this is true when the degree of f is bounded by log n by the van der Corput method, but but to go beyond that is what the main question is. Okay, and so and the third question is, so all these statements that I made work for the field f2 to the n sitting over f2. I mean, it right. So I'm pretty sure that all these things also hold for fp to the n over fp, where p is a fixed constant. But right, so I don't know. So what is the analogous statement to make for over fp, where p is a prime? I don't even know how to formulate the question. So when I work in fp instead of f2 to the n, there's no base field. So I mean, so sure, but yeah, right. So is there an analogous statement? Maybe that's the question. Or is there even a formulation of a question? You know, what are the functions of low complexity that resemble functions of low f2 degree? Right. So to formulate such a question and then to answer it would be nice. Right. That's it.